Hello, everyone. ZKGM. Thanks again for showing up at zkForge. I hope you're all well. I hope you're all learning new things with ZK and engaging with the community. And it's great to see that you guys are chatting in our Telegram and our Discord, and you have a lot of passion for ZK. And so today, we are going to be continuing. So the mentor we have for today is Harsh from Aztec Network. He's an engineer with experience developing a fully decentralized privacy protecting network. And today he'll be basically focusing on the theme of writing circuits and verifying proofs, here specifically DSL in Noir. So he'll take you through the fundamentals of ZK, why Noir. We'll look at Noir versus zkVM, and also cover writing an eligibility checker in Noir. So Harsh, if you want to take the stage, go for it. You should be able to share your screen now. I made you co-host. And thank you so much for being here.
Got it. Yeah, thank you. So yeah, thanks for having me here. And yeah, like I'm pretty excited. I've given versions of these workshops before. So I actually started this workshop back when ZK was pretty new, Snark.js was just out there. And I was just looking at my old presentation and I was like, damn, the world has changed so much, right? Like there's just so much that I had put in the future section of those slides that's already has happened in some capacity. And I guess back then, the tool I used to use to do that workshop used to be Circom. And this is like, like we are in the Noir world now. So, so I guess like just to give you some context, let me share my screen first. Uh, is my screen visible? Like, can you see that?
Yes, it's visible.
Cool. Yeah. So I think like the workshop is called Hack Your Way to Noir. And the only odd thing about this presentation would be that I actually have two presentations. So there are slides that I have lost access to because I created it with an email that I no more have access to, but I can still play them. So I would be mixing both of these presentations. Like I would use a lot of slides that I made right now, but then I would also jump to this other one here, which is slightly in a different theme, but I would be using it to, like convince you about few other concepts as well. So the workshop is called uh, Hack Your Way to Noir. And it's basically getting convinced that, like Zika actually works and you can write your first Zika circuit and you can do all of this in 45 minutes. Uh, so just to give some context, this workshop is basically for someone who's pretty new to the whole scene. Like if you already know pretty much a lot about Zk and you don't need a lot of convincing to be done, and if you've done like a lot of circuits before, like you probably might not find it as useful. It's for someone who's really new to the whole thing. But at the same time, at the end, I would be doing a Q&A and more than happy to answer anything there as well. So let's get started. Yeah. I hope you get out with your first Noah circuit from here, right? So who am I? I'm Harsh. I am right now a forward deployed engineer at Aztec. I do a lot of things there. My background is I worked as a protocol engineer at Polygon. That's where I got my first break into ZK. I was working on ZK DIDs there. I was one of the core engineers of Kakarot zkVM. It's zkVM written in Cairo. And then I also did a lot of research engineering at Fuel. So I've been in distributed systems, this whole ZK space and all of this for like, I guess now it's fourth year or something like that. And I'm yet not bored. So I think, I think like uh, quite a decent time in given like how old our industry is. But yeah, like so I'm Harsh Bajpai. I am a forward deployed engineer at Aztec. And what's the agenda for today? And yeah, we're not gonna invent AGI. Don't worry. I'm not gonna teach you how to write a neural network from scratch. We're gonna keep it simple for today. So it's going to be like speed run a little bit about Zk and arithmetic. So like in 10 minutes, I will try to convince you that this whole stuff can work. and I would give you a basic idea of arithmetic circuits and things like that. Then I would try to convince you that all this magic is possible. So the first bunch of slides is for someone who doesn't have any mathematical background, and they just need to be convinced that, like, it is indeed possible, whatever we're going to do later on. And then I'm going to talk about ZK VMs versus ZK DSLs, because I'm going to talk about Noir today, but there's also this other realm of ZK virtual machines. And I think they do refer a small section in this talk for them. We're going to write a first Noir circuit. We're going to keep it very simple, and then we're going to open it up for Q&A. So now comes the odd part of the presentation. Boom. Like, we are now in new slides, which look nothing like the old slides, but yeah, you would have to bear with it. Uh, yeah. So I think, like, basically this is kind of, like, what this meme kind of encompasses the feeling of everyone in who's trying to get into ZK right now. That, like, everyone is hearing about it, everyone wants to get in, but then everyone is confused, like, about what it actually even is. And let's just start with the very basic, like, what is ZK cryptography? And it's basically a way to prove knowledge of information without actually revealing it. That's like one way to think about it. Like, but that's where, like, if you're doing, like, talking about ZK stuff, that's how I would frame it. Although these slides are a little old, so I might change them a little bit if I had to write them right now. But yeah, you could say, like, one of the most popular use case for them is to, like, prove knowledge of information without actually revealing this. And the question is that what would such an interaction look like? You would have, like, two parties, and there would be a party called as a prover. There would be a party called as a verifier. Prover possesses some information, which is, let's say, some data, and the prover could basically want to prove to a verifier that, let's say, the data that they have satisfies certain constraints, right? Let's say it could be that my age is about 21. It could be something like these many blocks have been proposed and attested on Ethereum. And there's this verifier, and the verifier in this scenario only cares about the constraints around this information being correct. Like, they are fine even if they don't see the real data itself. All they care about is that you can prove some statement, and that's all they care about. So their interaction is that the prover has some piece of knowledge, and they want to create, like, some sort of a ZK proof, which they should be able to give to a verifier, and a verifier should be able to verify it without needing, like, any, like, real trust assumptions. Although in Snarks we do have a small trust assumption, but yeah, like, it should be cryptographically backed, and they use the ZK proof to communicate between each other. But then the question is, how is that even possible? Because I just made up a protocol where, like, there's this verifier, there's this prover, and everything is just gonna work. And let's take a small detour, and let's talk about computation itself, where, let's say, you could say a computation is a step-by-step processing of information. So you have some inputs, you do some processing on top of them, which is what we call the computation, and then you get an output. So one example could be multiplication of two numbers. Like, you have this processing, which is, let's say, z is equal to x into y. X and y is your knowledge, or it's basically the information that you're using to compute, and z is the result itself, right? Now, in a traditional sense, how do we verify computation? We can always recompute, right? So let's say the prover says, here's my input, here's my computation, here's my output. The verifier can take the exact inputs, do the exact same computation, and verify it. And basically redo the compute, and verification is done. But what about really heavy computations? And what about scenarios where you actually want to hide this data as well, right? It just doesn't make sense. So what do we do here? There has to be a way out from it, right? And that's where, like, say, this proof of correct execution of computation comes with. So let's say there's this notion of verifiable computation, where along with the, let's say, the output of your program, you can also create a proof of computation, which could or could not be succinct in nature for someone to verify, but it's only useful actually in a practical world where it's succinct, right? So where you could do a heavy computation, you could do a lot of heavy computation along with it, and that creates this new object, and this new object is called a proof of computation. And you can give this proof of computation to anyone, and they would be able to verify your computation by just taking the inputs, by just taking the outputs, and the proof of computation is going to take place. Like this object is just going to help you replace the whole recomputation phase itself. So how is all of this related to, let's say, like proof of knowledge, like zero knowledge proofs? Like what if you could hide some inputs in this model? So for example, in the old approach, we have some inputs, have a proof of computation object, and have an output, and you give a verifiable computation where like the other party doesn't have to rerun the compute, and they get to verify the computation. But what about this new approach where you could even like hide a set of inputs? And now what you're technically able to prove is that you have some computation, you have some output, and like you can verify whether the compute was correct or not. And you could even verify statements around certain constraints around like the input itself. For example, the computation could constrain something like that x has to be greater than 18, and that's a proof of your age. And now the input is hidden, so the computation is still proving that whatever x I had was greater than 18, but neither the input is available nor the other party needs to do the whole computation again. So in this model, you have a computation, you have inputs, you have outputs, you have a proof of computation, but at the same time, you have the ability to hide signals whenever you want. Like you can hide certain inputs, you can choose not to hide certain inputs. So for example, you could do factors where you could say that I know some number z, where I know two numbers x and y who when multiplied would result into z. And then x and y could be hidden. So for example, if I gave you 12, you don't know whether I have 2 and 6, whether I have 4 or 3, or whether I have 12 and 1, right? That piece is just hidden. So basically proof of computation plus hidden inputs from proof. And that's kind of like a computational model for proof of knowledge of inputs, right? That's kind of where you get this whole ZK thing from. So hello, ZK Snark. So Noir right now primarily works with Snark-based proving systems. They also Snark-based proving system. I can talk about them at the end if anyone wants, but this is gonna be pretty focused on the Snark-based one. So basically, ZK Snarks is one of these proving schemes that you can use to prove compute and also like prove knowledge of inputs. So and the way you do it is that you express these computations in these arithmetic circuits where you have gates do some sort of an operation, let's say addition, multiplication, and you basically have these inputs flowing through them. So it's basically like a real circuit, but it's of course like a virtual version of it, where when you execute this, apart from just coming to some output, you can also create a proof of computation. So yeah, like we use arithmetic circuits here. So you can create any sort of computation you want out of these formats. Like you can create hashing, where you could say that the pre-image of some hash, and without showing the pre-image itself, you could just prove it to someone. And one last piece of information, because I know like everyone wants to get into the programming side of it pretty soon, is the difference between like public inputs and private inputs. So as I told that like you can choose to keep some inputs private. It also means that you can choose to keep some inputs public. And okay, so that's it. Like you could have public inputs, your private inputs. Public inputs are the inputs that are visible to the verifier, and private inputs are just not visible to the verifier. So the verifier can only be satisfied around the constraints around private inputs, but the verifier can see the public inputs in their original form as they are. And that leads to the question why someone would even want like public inputs. Basically, there are use cases where they're really helpful. So for example, if I want to prove that I am part of an NFT whitelist, well, I would want to hide my address that is in the whitelist, but then the verifier needs to make sure that you are actually part of the NFT whitelist that they consider to be legit. So in this circuit, there would be two inputs. Like one would be the address of this person, which would be a private one, which they could prove through some sort of a digital signature. And the other input would be this whole NFT whitelist. And this one would be public, so that the verifier can see that your address actually belongs to a whitelist that they consider as legit, that they find is canonical or something that they believe in. Uh, oh yeah. So does anyone had a question? Like I heard like something from a mic. Okay. Okay. Cool. I will go ahead. And then the flow of doing these computations is like writing ZK circuits is pretty simple. Like you basically generate a set of wait a minute, like this slide. Oh yeah, I think like this is kind of like we have actually crossed it. Yeah. So build time. Let's try to build something cool. And now this is where we would get away from the old part, right? But I would like still give you this model of what is gonna happen. We are gonna write a circuit. We are gonna compile it. Okay, before we get to the slide, there's like this two pieces of information that we have to get to, and then we can get to it. So like how do we write ZK programs? And there are two ways you can write a ZK program, right? So now this is the new piece of information that has really changed back from the time when I showed you that last presentation, where like ZK VMs weren't really a thing. It was all Circom and GNAC, and like also used to be something called I don't know, Socrates or something like that. I can't remember it, but that's all there it was. Like it's the only ZK VM back then was Maiden, but it was too early. But yeah, so one way to write your ZK programs is via a ZK VM, where you write your computation in a high-level language like Rust, C++, and then you give that computation as an input to a ZK VM. The ZK VM executes it, and then the ZK VM has its own ZK circuit that can then prove any computation that's run on top of the ZK VM. So this way, there's only one circuit, which is the ZK VM circuit, and you only prove the ZK VM circuit with some proving system. You get out a ZK proof. So you just have this one circuit and this one VM, and you write computation for this VM, and you are able to do provable computation. So examples would be SP1, RIS0, Cairo, which is, let's say, a custom ISA. There's Lita, there's Maiden. They're like now too many, like Airbender from ZK Sync. So I think like I'm pretty sure someone is just inventing a new ZK VM out there right now. So yeah, about ZK DSLs, so they are like little simpler in terms of the whole pipeline, where you write your computation in a DSL like Noir, Circom, and you could even like technically use something like zkLLVM to write them in Rust. But let's just stick to, let's say, Noir and Circom. Every computation has its own unique circuit. So every computation results into a new circuit. That circuit is specifically for that specific computation. And then you use a proving system to generate a proof of that specific circuit. So there's no intermediate VM that you're trying to target. You just write your computation and you directly get a circuit out of it. And the examples would be Noir, Circom, Pilcom. I would even put zkLLVM in this category. So yeah, these are like the examples of it. And to just do another comparison super fast, zkVMs, high-level programming languages, zkDSLs, domain-specific languages. zkVM, there's only one circuit, that is of the virtual machine that runs this computation itself. zkDSLs, like basically there's one circuit for every computation that you write. Third in zkVM would be that to change the proving system that you're using for your computation means to change the proving system for the virtual machine itself. While in the case of zkDSL, like the languages target ideally some sort of an intermediate form. It could be ACIR, it could be R1CS, and you basically have to just find a proving system that's a prover that uses another proving system and is compatible with these formats. So I would say that switching is slightly easier, at least from my perspective, in terms of proving system on zkDSLs. zkVMs, the programs can sometimes be less optimized because you could be constraining a lot of things around the VM that you might not need. zkDSLs could be very optimized because the only constraints that you have in the computations are about what you're going to prove. So let's say zkVM, the example would be, again, we already talked about it, so not going to repeat this part further. And yeah, Noir. So that's what we are going to write today. We're going to write some Noir today. So it's a zkDSL from future. It has a Rust-like syntax. It compiles to this intermediate form called ACIR. So any proving system that's compatible with ACIR should be able to support Noir. It can work with any proving system that supports ACIR. It has a rich standard of libraries, language features. It has a rich ecosystem of applications and has a really big language community. And of course, it's maintained by the OG Aztec team. So that's why it's my favorite ZK DSL out there. Yeah. So now let's go and build something out with this, right? And I'm kind of like not thinking of it as something which I think most people would be following along, because I've seen that most of the time people fail. So you can just watch and it's very simple and you can do it later on yourself. The things that you would have to understand is that I would like you should go to Noir's documentation. I guess post this workshop, people can provide links for them. And this like very simple installation kit. There's this tool called Noir, and if you install Noir up, that would give you access to Nargo and everything else. So there's this, uh, yeah, there's this installation guide, and you can follow it. Another one would be that you will need to install the our BB Prover. I still have a hard time pronouncing it. It's either called Barrettenberg. Uh, but yeah, so I think that's the proving backend that you would have to install. It's Aztecs Prover. It's written in the Epic C++, and right now, I guess it supports the Ultra Honk proving system, and it's very well gelled together with Noir. So what is that we are going to write? So there's this GitHub repo that I've made, and you can probably just clone it. Yeah, you can clone it and probably like follow along with however you want to. So let's say, okay, yeah. So workshop, and I'm gonna clone it. So like the step one would be that we'll clone this repo, and yeah, and then we will just open it in Visual Code, and that's what your repository will look like. So I hope the font size is fine. I will still load it up a little bit. So you will have these, yeah, you will have all of these various files in it. And I think the default branch would be something called complete, but you should switch to main. Yeah, so you should switch to main because the default branch, okay, yeah. So the default branch here basically has the whole complete code, but main is where the boilerplate is. So now I'm on main, and when I would look at my main.noir, which is like the place where you would write your circuit, you can see a very simple boilerplate code written here. Now, nargo.toml is a file. It's a file that declares your Noir project. So, for example, the name of my project is Noir Workshop. It's a binary file, which means it's an executable circuit. And yeah, like it's just like a rest.toml if you're very familiar with it. And then there would be this file called prover.toml. That is where you give the input to your circuit. So, for example, our circuit takes a single input, which is a field element, and you just provide it here. Okay, one thing that you see in the circuit is that we have this data type called as a field. And what is a field? So every proving system works on top of finite fields, and every finite field is basically, like a finite set of elements, and you basically do arithmetic in them. So like mostly these are prime fields, and the field could be any size. So here, let's say the field would be whatever is the bit size of the field that you're operating in with your proving system. So let's say there is BB prover, there could be some prover that could be working with 31-bit, 31-bit, field elements, and depending on that, the exact value that the exact type that this represent changes from proving system to proving system. Right now, we are going to use Ultra Honk. I think it has like some 252, something like that, like more than 250 bit of of field element size. So that's what it represents here. So our circuit, what we really want to do with it is that we want someone to have an ability to be able to prove that they know an element that belongs to this array. And if you are thinking where this would be useful, it's basically being able to prove a membership in a set. So right now it's very simple. Like you could just put a number and it will tell you whether it belongs in this array or not. But in a real world scenario, you could basically have someone provide a digital signature through which they're trying to provide the fact that they know a public key, they know a private key, whose corresponding public key is in a list of a set of allowed public keys. And that would allow someone to check that this address belongs in a list of addresses without even knowing that address itself. So, for example, this could be used for whitelisting and a lot of other things. Although the truth is that you would use some other data structure for this, like you would use some sort of a Merkle tree. You won't use, like you won't use like a array for it. Not the best way to do it. Not the best data structure for it. But yeah, but just trying to keep it simple here. We're going to use an array and we're going to write a computation here with Noir that's gonna try to prove that whether you know an element that belongs in it or not, and it has practical use cases in expanded forms where you could prove any sort of membership in any sort of a set. So right now, our input does not have any visibility modifier with it. So what I mean by that is that if I add this word public here, it means that it's publicly visible now to the verifier. So the verifier would see what the input was. And if I hide it out, it now means it's private and the verifier cannot see my input. And then what I'm returning out from the circuit is this Boolean value, and it's a public value. So the verifier can see what this response is. So we are going to just return true or false. Every time we return true, it means that so every time we return true, it means that this element input belongs to this an element in this array. Every time we return false, it means that it doesn't. And the verifier, just based upon this one public value, can find whether I have some legitimate input or not. So how would we write this? So the first way would be to declare a variable, and this variable to declare an identifier that could like keep reference to this value. So we are going to call this AR has input, and it's a Boolean value. So we have like very rich data types in Noir. You have arrays, you have vectors, you have Booleans, different types of integers, U32, U128. So you have like all sort of rich data types. You have hash maps. So the standard library is really vast, and I would definitely suggest looking into the documentation for it. Right now, I'm just going to keep it simple. But if you have written Rust, I can say you already know 90% of Noir. It just looks like Noir. It just looks like Rust. So yeah, that's it. And we're gonna make this default value false. And then we're gonna write a loop. And that's the thing, like post this whole GPT Claude stuff. Now you're just tempted to do a tab and complete it all. Although I will try to resist that temptation. But yeah, so the for loop looks very similar here. You will just say for, let's say, I and the length ARR len. And what this basically means is that iterate. Okay, this is digital len. I think it's let I or something like that. Okay, I would have to quickly check, I guess. Syntax. I'm really bad with syntax. But there's the syntax for the Noir language, standard library, concepts, types, arrays, and then there is this length thing somewhere here. Oh, wait a minute, like it has to be in control flow. Well, I'm doing it correctly. So let me check. Or I and our length. It could be that it's not a property. It is. So that's weird. Is it just the fact that it does not have false? Okay, just a second. Let me see what's going wrong here. It's definitely something pretty silly. But the good thing is that I at least had a working solution somewhere here. So I can do git stash and just see what's going wrong here. It's for, I see. I'm missing the two, yeah, two dots behind. Okay, check out name. Okay, guys, I cheated a little bit. Sorry. I guess AI has spoiled me. But yeah, basically you're gonna do, yep. And now what we are trying to do is that we are trying to iterate through all indexes of this array. Yep. So we're trying to loop through all indexes of this array. And what we want to do is we want to, just a second, I lost. Yeah, okay. So now what we want to do here is that we want to check that if a value at this index matches to this input value. For that, we are gonna have this thing called let ARR has input. It's a Boolean value, and it's by default false. It means that we are by default assuming it does not have it, and you're just gonna return this value here, right? Now, yeah. So what we will do is we will say ARRI is equal to input, and if this is true, then we're gonna say it's true. Now you will see that I'm getting an error here, and that's because I have not made this value mutable. So if you remember your Rust, if someone is familiar with Rust, unless I explicitly declare that this value is mutable, I cannot change it. So it's basically for like before you declare a variable, you have to declare whether it's a mutable one or it's a non-mutable one. And if it's not a mutable one, which is what it is by default, then you cannot change its value later on. So I have to, let's say mute. And now that's it. We have a small mini circuit, less than 50 constraints. And what all it is doing is that I will give it an input. It will give back a Boolean value, which would be either 0 or 1. Yeah, it will just tell me whether my input belongs in this array or not. And it's like a very small hello world equivalent of it. So the first step here is that now we have to compile the circuit. So we'll do go compile. And it will, if you have seen, like it has created this compilation, and there is this like this JSON file now represents my compiled circuit. So you can try to take a look at it, but probably won't make much sense to us, to be honest. Okay, cool. That's thing, like, so the compilation has happened and it compiles it to this ACIR intermediate form. Now, the second thing is we need to provide the input. For that, you can use this command called nargo check. It will create this file called prover.toml that already exists for me. And you can provide any input here for this value. So let's say this specific input value here, whatever you will provide is what the circuit will be executed with. So firstly, I will try to execute this circuit with the value 7, and it should return false, right? So it should return 0 at the end of it. So if I do nargo execute, okay, I think, yeah. So you can see that a witness was generated. So basically, a witness is something that a prover uses later on to create a zk proof out of it. But you can see the circuit output is the field element 0, which means it's false. But if I go ahead and if I try to, like put something like 2, which does belong inside this array, then when I would go ahead and I would execute the circuit, it should be true. So for example, now I'll go execute, and now I can see that the circuit output is true. So now this is, you see this new thing, which is like a GZ file, and it's basically the witness of your circuit, which later on is a piece of information used by the prover to create a ZK proof out of it. So if we want to ZK proof it, the way we are going to do it is we're going to use this BB prover that Aztec provides, and it's an ultra honk prover, but you could technically use any prover that's compatible with ACIR. And the first step that you're gonna do is you're gonna generate a proof. And I think, yeah, so that's the command. You're gonna see gen proof. You're gonna tell it where the circuit lives. So I'm gonna say this is the circuit. Yeah, I guess this will be coming up. Yeah. So this is where the circuit is, which is in the target file. Then I'm gonna provide my output. I'm gonna provide my witness, which would be this GZ file that we have, and then I'm going to provide where do I want the ZK proof to be, and that would again be the target directory. So boom, like the ZK proof is done, it's saved here. There's this proof file, there's this public inputs file, and the public input file would just have this value so that the verifier can check whether like you had some correct input or not. And the proof can now be used to like without any communication, non-interactively verified. So let's do a verification of it. So the first thing that you need is a verification key. So uh, you can use this thing called write. Yeah, you can use this command called write a verification key from the prover, where you're gonna say the circuit lives here in target directory. It's called noir.json, and write the verification key to the target directory. And now you can see we have this verification key here, and we can now use that to verify proof. So we can say verify. We give our key dash key k, which is like target verification key, and then we give our proof, which is like in target directory again, and then we give our public inputs, which here would be just this specific boolean value. And when I would go here, it's verified. So that's an end-to-end demo of like using Noir to write a circuit. Uh, that being said, like one interesting thing about this thing is that regardless of how big your computation is, the verification will always happen in constant time, and that's a property of Snarks. That's really cool, to be honest. So I think yeah, that was about writing some Noir. uh, I would say thank you really much for spending your weekend with me. I completed my challenge of keeping it under 45 minutes, so it's only 37 minutes. Subtracted 2 minutes for whatever introduction I did. So yes, I guess like I did an Eminem of a ZK workshop, and I'm now more than happy to like help answer any questions that anyone has.
Yeah, we have time for questions. So yeah,
Uh,
Austin.
yeah, sure. Hey, Harsh. So I just wanted to check like how much of the innovation is that is still going on in ZK is happening on the DSL side, and how much of it is actually happening on the side of like say new circuits being created, and or has the sort of the math around like how circuits are written and how circuits are created already sort of reached its peak, and therefore now it's time to make more DSLs and such as and good ones such as Noir. And if there is a better sort of circuit and arithmetization scheme that comes out in the future, will that impact the current DSLs?
Yeah, that's a good question. Like that's something that interestingly I was researching yesterday itself, where I was trying to research, like what's the state of the art? Are people trying something really new? And I think like so this the founder of Blockchain has done some really interesting research in the ZK space itself. Like I was hearing to a podcast where he mentioned something very interesting, that most of the efforts that have gone into like into like making zk faster has been on the side of creating better proving schemes, which
Hmm.
means like basically committing to polynomials more efficiently, and less of it has actually got into creating languages that I automatically create a very small footprint of like polynomials that you have to evaluate and prove. So I think right now, I still think there's a lot of work that's like Zeek is nowhere where its state of art should be. Like that's what I believe. It's relatively very new. Every second, third day, I'm seeing people come up with something really new. Like I was looking at Ligero. It's also pretty cool. Like they claim they can do 10,000 Poseidon hashes per second. And then, so yeah, so I would say that right now we're going to expand both sides. Like we're going to see more better proving schemes coming up, people coming up with opinions, stuff like circle stacks. At the same time, we're also going to see some improvements on the DSL side itself. So I was looking at, I guess, the NOC VM, and there's this language called Hoon, and they claim that, like basically NOC VM, I guess, and their claim is that it creates very efficient circuits. So I still have to verify that claim, but it looks like there's a lot of work going on in that direction as well. Ligeri too, I think, is something that someone made to combine with Ligero, but Ligero is like another one. So I think they're like two versions of it. Like someone wrote it in the comment. Now, that being said, what does it mean for existing ZKDSLs? I think like the good part of a ZKDSL like Noir is that it's very unbiased towards the proving system that it targets. it just emits this intermediate format that is ACIR. And let's say if tomorrow there's a better proving system out there, they just need to basically be able to prove these ACIRs, like be compatible with this intermediate form, and you should be able to, like get all the benefits out of it. So yeah.
Smart, smart. Yeah, awesome. Thanks.
Yeah. I guess like more probably. That's a good.
Hey, thanks for the lecture. That was great. I was wondering, I've seen few documentation about Noir and Aztec also, so I wanted to know how tightly coupled is Noir. For example, you develop your circuits in Noir, and for example, you can verify, I guess, from Barenterberg, right? The proving, and also Aztec. So how tightly coupled would that be, right?
So is your question how is Aztec related with Noir? Like, is it
Yeah,
that?
yeah,
I,
yeah, yeah.
I see. Yeah. So basically, like Noir is an individual effort from us to like make the best zkDSL, best way to write ZK computations out there. And then basically the good property of Noir and our proving system is that it works really well on mobile devices and it's client size compatible. And it creates very succinct proofs for verifiability. So that's why we also use Noir combined with the proving system itself in Aztec, where we have written basically the whole client-side proof generation happens on Noir circuits. Then the Aztec virtual machine, where all the public code gets executed, is again basically proved via Noir, which is interesting. And the whole Aztec protocol is again written in Noir. So the whole runtime that you get in Aztec, which is let's say this memory, you get the storage and access to all of these things. That's also later on provable via Noir circuits as well. So you could say Noir is something that we have independently created, and we use it in creation of Aztec itself, which is proving the Aztec rollup itself and also proving our client-side proofs.
Awesome, very, very clear.
Yeah, Sanjay. Right.
Yeah, Harsh, thank you for the great session. Actually, I'm currently learning Nova and building the project regarding it, and I want to get into the ZK ecosystem. I know it's currently like evolving right now. What are the steps do we need to like get into to land a job like that? Basically, like need to focus on Nova or like should focus more on Rust and low level programming for building the circuits maybe.
That's one of the hardest questions to answer, because the thing is that, like, I really don't know. It's probably some sort of a career advice that you want, but I really don't know what's going out, what are people hiring for. But like personally, I can say for me, following my curiosities have served well. That's all I would say. Uh, but really, I really don't know. Yeah, I would say that like learning Noir is something that's really beneficial, because I know a lot of ecosystem teams out there, and there are a lot of funded ecosystem projects. But if you want to get into zk, I would just say that it's better to get firstly, or like if you want to work as let's say some sort of a core protocol engineer here, like you would also have to like be really well and proficient with like other things as well. And what I mean by that is knowledge of polynomial commitment schemes and like various arithmetization, some security features, like how do you constrain things, because these are things that really matter when you are trying to write a secure ZK program. So I would say, yeah, I would say Noir is cool. At the same time, what should you learn from a career perspective? Really not the best person to answer. Yeah.
Thank you, sir.
Yep, Sebastian. Like,
Many questions here, but related as the thing that you already mentioned, what level of mathematics are required because as you said, maybe it's better to first learn mathematics and build on top of Circle and continue with CK, these CK DSLs like Noir, if you want to build a real product. But if you want to learn the protocol engineering stuff, I think, as you say, so what level of mathematics is required?
Yeah, that's a good question. So I would say that, by the way, like when I said you should learn it, like that was because he was like asking it from a very career perspective of it, like but I do think you can, like, right now itself with Noah, write a lot of meaningful projects. But at the same time, I would say that it's better if you invest some time understanding what's happening under the hood, because that would that will make sure that you're not interacting with a complete black box. We just don't know what's happening. Although that's what programming systems is supposed to be. But personally, like, I like to know what's happening under the hood. Now, what level of mathematics you need to know? Honestly, not much. Like, just basic finite field arithmetics, polynomials, stuff like, Lagrange interpolation, know some basic rules, some like important lemmas around polynomials, and that should be it. Like, I'm pretty sure that you can easily teach it someone even who's like out of high school, because it's not some rocket level maths, it's not calculus, it's just a bunch of abstract algebra. So yeah.
Hey Harsh, I was wondering, would you be able to come to our Discord and maybe answer some of these questions that people have? Because I don't think we'll be able to get through all of them right now with
Yep.
the time that we have remaining. So yeah, would you be available for that?
Yeah, I can asynchronously keep answering them, like there as
Yeah,
well.
that would be great. Let me provide you the link to our Discord. Yeah, guys, if you could please go to our Discord and post your questions there, and Harsh can answer them asynchronously. That would be really great. Probably makes the most sense right now to get through all of your questions.
Yeah. Okay, cool. Because a lot of people have asked me about the math side of it. I will leave you just with this one resource that I have, like, I kind of would say that it's basically like, if you have read this, you're good enough to understand how Planck's, or let's say all these maths work. This is called Moon Math Manual. You can read it. It's open source. It covers everything. It builds all of your foundational knowledge. So I think for everyone who's curious to know how much maths you need to know, like, this is enough to get started. Although, like, you can just use Noir and write any stuff that you want right now, but I would definitely say learn some stuff that goes under the hood as well. It always serves well. Yep.
Okay, maybe one more question, and then we'll move to Discord.
Yeah. Yeah, on Discord, like, I might not be able to answer them right now. If you can send me this link in, like Telegram, it would be better, because I'm really scared to click a link on public chat. Like, I don't know it.
Yeah,
But it
sure.
really,
I'll send it to you on
yeah,
Are you on Discord?
Telegram, no problem.
yeah. Cool. I guess, like, we had this question from Conquest. I will quickly take it, and yeah.
Okay. Good afternoon, Harsh. So you said something about understanding the hood and works. What did you mean by that? I think Noir is like the most widely used.
I can't hear you.
I can't hear you, like, you. But
Am I?
I just, like, you can probably write it in this comment.
Okay. Okay. No problem.
Yeah. Okay, I guess Sebastian will just take your question here and probably end it, like.
Okay. So my question is, you mentioned the Cairo way. What does it mean?
I guess, like, I mentioned the Cairo virtual machine. So it's something from the Starkware team, where, let's say, there is this language called Cairo, which compiles to their zkVM, which has a specific ISA, which is the Cairo VM, and then they prove it through Stu. So that's what I meant here. Yeah. So I guess, like, I am in here. I have Basically, I can just text somewhere. I will just chat. I've just texted in general chat, hello, Harsh here, and you can just, like ask anything tagging me, and I will try to answer whenever I'm available on it. So,
I have a question.
oh yeah.
Okay. According to building real world application in today's world, what is the most used framework when it comes to zkForge?
Yeah, that's a good question. I would say right now the most it has actually changed. So the ZK world isn't like very art like it isn't like that sticky as people think it would be in terms of stacks. Like I've seen teams move off from Circom to Noir, but I would say a lot of it is in Noir. I would say a lot of it is in GNARC. A lot of archaic stuff would still be in Circom, and a lot of stuff in Cairo. And then now people are slowly also moving to zkVMs, which is like SP1 and RIS0. So I would say like these are like some of the serious contenders on top of which serious infra is being made. I would say most of the privacy stuff is going to Snux. So Noir is where like it really shines out. And most of the scaling stuff is going to Stocks, where let's say Cairo, SP1, RIS0, like stuff like that is coming up. Yeah. Cool. Oh yeah, I just like I can take one more question. I don't have any issues. Like I can be here for more 8 minutes. Like I guess but yeah, like go ahead, David. Yeah, like whether I'll be done.
Hey, hello, Harsh. Thank you so much. I was wondering, I think one of the most important things about Aztec and Noir is being like true zero knowledge in terms of privacy.
Mhm.
So my question is like, what are the specific features about this privacy, true zero knowledgeness things? Like, is it just to set the private inputs? Does it has like a trusted setup? Can you tell me what makes it more private? Thanks.
Mhm. Yeah, technically you can even do like private stuff with like stuff like stocks. But the special properties is that number one, with let's say the proving system that we advocate for at Aztec, which is Snux, is that you have a constant verification time. And from my understanding, and I could be wrong, so if I'm wrong and if some cryptographer is listening to it, please DM me in private that I'm wrong. But from my understanding, this comes up from the polynomial commitment schemes that we use, where we have a trusted setup assumption. So that's why, like we get this constant verification time. So we are not beating information theory. There is that assumption out there, but you can do a lot of cool stuff around the ceremonies and get to like very decent confidence around them. So yeah, with Snarks, like the good thing is that we have seen that they can work very well on low RAMs while proving. They can verify in constant times. And it turns out that if you want to do privacy, you would be executing the circuits on user devices. And if you're on user devices, you are limited by the amount of RAM that's out there on mobiles. And if you want to verify these proofs, you don't want them to be these big chunky proofs because you would have to route them through a network. So it's better if these are like constant time proofs and constant size proofs. So that's why, like they are more beneficial for ZK stuff, although you can do ZK with other proving systems as well.
Thank you. Very clear.
Okay, cool. I would say, yeah, it was pretty fun. Like, feel free. I've like dropped some message in Discord. Feel free to tag me and just at the rate me and ask me, and I will try to answer.
Are you active on Telegram or Discord?
Yeah, you can just text me on Discord. Like I've dropped a message on Discord general chat at that group, and yeah.
All right, thank you so much, Harsh. That was a great presentation, and thank you everyone for showing up and showing commitment to ZK. And yeah, we'll see you next time, and see you in the Discord channels.
Yep. thank you everyone for joining, and like spending your time doing, not touching grass and sitting again in front of computer on a weekend. See you around. Yeah.
Have a great rest of your day, everyone. ZK, goodbye. Yes, ZK, goodbye.
Bye.